Hello and welcome to Practical Quantum Programming Part 2, a second in a series of 3 tutorials from DWave Systems Incorporated. I'm Joel Gottlieb and I'll be your host for developing QUBOs and embedding. So hopefully you've had a chance to listen to the first tutorial about DWave and about QUBOs, that is binary quadratic models. And the second tutorial will build on that material and show you how to begin to build your own QUBOs for your own problems, and then we'll explore the topic of embedding on the DWave quantum computer. So without further ado, let's get started on Practical Quantum Programming Part 2, Developing QUBOs and Embedding. So as a beginning, let's think about a very basic problem. And this problem will turn out to be underneath a lot of the much more complicated QUBOs that people build. So the basic problem is, suppose I have a map and maybe there's a region in the map and I have to assign one color to it, and that the color can be red, green, or blue, but it can only be one of them. I don't want it to be 2 colors or 0 colors. I do need to assign one, and just exactly one. And so this is an example of what is known as an exactly one problem or a one hot problem. The binary variables, let's just call them R, G, and B. You'll remember from the previous hour of the tutorial that we do binary variables for this quantum computer. And so we'll call them R, G, and B. And each one of them will equal 1 if the region has that particular color and 0 otherwise. So for example, if the region is red, then R will be 1, and G will be 0, and B will be 0. And obviously you could extend this easily to more colors. But how do we write a mathematical function which is minimized when exactly one of R, G, and B is turned on? You might remember from the previous unit that we always look for an objective function to minimize, something that mathematically the computer can seek out solutions for and find the lowest energy. So how do we write a function which is minimized when exactly 1 is turned on? Not 2 and not 0, just 1. And a solution to this problem looks like this. And I'm going to just show it to you and then convince you why it works. The QUBO function for this is 1 minus R minus G minus B squared. Now, first of all, why is this squared? The reason is that if I don't square it and it's just linear, if you think about what happens, let's say when all 3 are turned on, R, G, and B, the 1 minus R minus G minus B would be minus 2 if I did that. And I don't want that. I want it to be minimized when just 1 is turned on. Also, if I put 0 of them in other words, just 1 minus 0 squared, that's 1, that's not going to work either. And so picture in your mind a parabola, a curve that's higher on one side and higher on the other, and then has a minimum. The problem landscape, if I do that, then exactly 1 of these being turned on will be the minimum, and that'll be the minimum at 0 for the total. And you can, just sort of think about that in your head. If I set R equal 1 and G and B to 0, then 1 minus 1 squared is 0. And that's what I want. So it's a parabola. And now when I do the algebra for this, it turns out to be 1 minus R minus G minus B plus 2BR plus 2GR plus 2GB. And there's no squared terms. And where did the squared terms go? In other words, where's R squared and G squared and B squared? And I'm assuming that you're familiar with multiplying out 1 minus R minus G minus B times itself, which is, you could use the FOIL method or write it on top of itself, however you do math like that. But it turns out that the squared terms went away and canceled out because in QUBO arithmetic, r squared or g squared, they equal just the linear term. R squared equals r and g squared equals g. And you can do that in QUBO. You can't do that in Ising. So the formula would look a little bit, Ising. The formula would look a little bit different in the Ising model. But that's partly why we do QUBO. It looks a little bit simpler. So that's where the squared terms went. And then you also may, if you watched the previous tutorial, you might remember that when we wanted the qubits to have different values, we submitted a QUBO that looked like -1, -1, 2. -1 on the linear terms, 2 on the pairwise term. And that's in this QUBO. So basically what we're doing is we're finding solutions which are one of them turned on, but not the others. And this is a very important problem, as I mentioned. Now, if I write a small Python program in the Ocean API and submit it over Leap, as we discussed during the last tutorial, I get output that looks like this. And let's hone in on that first row. Blue is 0, green is 0, and red equals 1. Is that a solution? Well, yes. We talked about wanting there to be just one of them turned on. And that's called the ground state solution. In this case, the way I formulated it, in the way I wrote it, it has energy -1. So I must have put a constant of -1 there in the program. And you learned about the constant in the last unit as well. Now let's look at the second row. Blue is 0, green is 1, and red is 0. Okay, that's another solution. And theoretically then there should be one more. Blue is 1, green is 0, and red equals 0. And that indeed is a solution -1. It's also a ground state. Now, are there any more ground state solutions? In this case, if you think about it for a moment, no, because the ground state solutions are just having one turned on. But let's look at that fourth line. None turned on. See it there? Blue is 0, green is 0, red is 0. Nobody's turned on. And that is called an excited state. And it has energy of 0. And does the excited state have an expected energy? Yes, it does, because that's the penalty associated with violating the constraint. We wanted the constraint to have one on. There were none turned on, and that's the energy of 0. And also, if we look at the fifth line, there green is turned on and red is turned on. So that's a solution where we've turned on 2, one too many. And it looks like that the sixth line and the seventh line are also examples like that. So do those show the expected energies? I think so. And then look at the bottom, just for the heck of it. Blue, green, and red are turned on, which has 2 violations of the constraint. I wanted only one of them turned on, so that has energy 3. And so these are the 8 solutions for this particular very basic but important QUBO. And what I'd like to introduce now is a set of steps that we follow when we want to generate a QUBO. And this applies to Ising models as well as QUBO. Start with a problem in the real world, whatever problem domain it's in. Write a minimization function, the objective function, that incorporates the constraints, the rules that is that we have to follow, the objective, which is what we want to minimize. And then we bring them together in a general form. Something to be minimized is an objective plus the constraints, but we have to multiply the constraints by a number, which is known as the Lagrange parameter here, written as a gamma. And the Lagrange parameter is kind of a fudge factor. If you think about it, the objective might be a number with units like miles, things like that, dollars, whatever it is we're doing. And the constraints, as we saw in the previous problem, they don't have units. They're usually this many of whatevers. And so we can't add those two things without some number to get them into the same units and same dimensions and so forth. So we'll see what this gamma does as we go forward. So to go over this process, we're going to write our problem out in the objective, that is, objective and constraints in the problem domain. We convert them to math statements with binary variables, and we already did that with the one hot problem. We make them QUBO appropriate, and what that means sometimes is algebra, as we'll see, some way to reduce it down into a problem which looks like a QUBO that can be submitted to DWave software. The objective is a minimization function. The constraints are satisfied at their minimum values. Combine the objective and constraints, and then we've got a QUBO that's ready for programming. So let's introduce another very basic problem here so you can get the idea. Choose the pair of boxes with the smallest sum. Now, all of us can do this in our heads. There's no doubt about it. You just take all the pairs of two that you could make, the first and second, the first and third, second and third, etc. And you can do that very quickly, but I would challenge you that when there's a million boxes, you're not going to be able to do that. So this is the type of problem that the quantum computer can help us with, something where it's too many for our minds and then too many even for traditional classical computers. So the first step is going to be write out our objective and constraints in the problem domain. And the objective is minimize the sum of the boxes chosen. Okay? In other words, the numbers that are in them, add them up and minimize that sum. So if I take, for example, 1 and 2, that's 38. That's 17 plus 21. You get the idea. The constraint is that I have to pick exactly 2 boxes, not 3, not 1, but I want to put a constraint on that 2 is selected. And so we've got an objective and constraints. And here's step 2 of the process. Convert your objective and constraints to math statements with binary variables. Okay, so the binary variable we'll use for this problem is x sub I equals 1 if box I is selected and 0 otherwise. Okay, much like the colors that I chose. In other words, x sub 1 for box 1 is going to be 1 only if that box is selected. So my objective function that I want to minimize takes a second to think about, but 17x1 plus 21x2 plus 19x3, and if you think about it for a minute, you see that if x1 is 1, then the 17 counts in the sum, but if x1 is not 1, if it's 0, then it doesn't count, and that's how this works. You're just multiplying each one by its weight, if you will, is the number that's in the box. The constraint then for getting 2 of them turned on, much like we had in the one hot problem, is x1 plus x2 plus x3 equals 2. So now I have an objective and constraints. Now the third step is make your objective and constraints QUBO appropriate. In this case, we really don't have to do anything other than write the constraint as the sum of the x's minus 2 squared. And that's the same form as it took in the one hot problem earlier. If I do that, then it'll favor having two of those turned on, but not 3 or not 1. Notice the number 2 in there instead of the number 1 in the one hot. So if you like, this is 2 hot. I have wanting 2 of them to be turned on is my constraint. Then in the process, we combine the objective and constraints, and that's just min of 17x1, etc., plus some number gamma times x1 plus x2 plus x3 minus 2 squared. And now this QUBO is ready for us to write a program for. Now we're going to leave this one unsolved at the moment, but I encourage you to try it. And I'm going to show you another one now to sort of keep whetting your appetite to solve these things. But I encourage you to work the algebra out. I end up having to do it actually for each one every time because I forget. But I encourage you to work the algebra out so you get used to it. Even on the simple problems, I learn a lot from them. And here's another basic problem to try. You have a set of 5 numbers, 1, 2, 3, 4, 5. Find 3 numbers in the set A which add up to 8. Okay, so how would you do that? You're going to follow these steps. Think through what this means. They add up to 8, so that's a sum. So go back to those previous few slides. And then I said 3 numbers, not 2, not 4. So that's a constraint that I want exactly 3 chosen from that set. So can you write this? I want you to put me on hold for a little while if you're watching this on the web. Put it on hold for a few minutes and think about that and see if you can come up with it. So rather than show you how I got it, I'm going to try to motivate you to write your own program after you've signed up for LEAP, of course, like we discussed in the previous unit. But I'm going to instead talk about the output that I got when I ran the program that I wrote. If we look at the first row, notice that the 1 is turned on, the 3 and the 4 are also turned on, and the 2 and the 5 are not. And the solution is 1 plus 3 plus 4 equals 8. Is that 3 numbers that add up to 8? Yes, it is. Is it exactly 3 numbers? Yes, it is. Notice on the second line, 1 and 2 are turned on, and so is 5. And that's 8 also. And notice then that there have been 2 solutions. The ground states have energy minus 73. Are there any more? Are there any way that I can take 3 numbers out of these 5 and add up to 8? And I don't think so. Do the excited states show the expected energies? Notice that they're minus 72 and so forth. I believe they do because the penalty associated with missing one of those constraints is a 1. It adds an energy of 1 to it. If we do that from the ground state of minus 73, then I get minus 72. So it looks good. And if you look at the third row, notice that it's 1 plus 2 plus 4. That's 7. Oops, nope. That's not quite the solution that I wanted. Hence, it's penalized. And notice also then in the fourth row, 3 plus 5 it's 8. So that satisfies that constraint. But that's only 2 numbers. 3 plus 5 is not sufficient because it adds up to 8, but it violates the constraint that 3 numbers should add up to 8. And for extra credit, can you explain where that 73 comes from? And I'm not going to show you that here, but it turns out to be related to the constants in this problem. The fact that there's an 8 and the 8 gets squared leads us to a constant. But I'm going to go on after that and leave that for something for you to think about. Instead, I'm going to go on to one more problem, and this is a bigger one that was solved in the Andrew Lucas paper that I mentioned in the first unit in the tutorial called graph partitioning. And this is going to take us a while, but I'll give you an illustration of how a more complicated QUBO works. The problem specifications are, I've got a graph G, and I want to split the graph into 2 subsets so that, part 1, the subsets are the same size, and there are as few edges as possible between the 2 subsets. So basically we're trying to divide up this thing into two blobs so that there's as few links as possible between the two blobs. So in this case, and this is an easy graph, which we'll talk about coming up, but I've split into a red and a yellow, and in this case there happen to be 4 connections, and we'll talk about that later, how many we expect. But the idea is to divide up the graph into 2 blobs with as few connections between the blobs as you can get. Okay, so QUBO step 1, get our objective in constraints. In this case, the objective is minimize the number of edges between the subsets, so we'll have to count those. And finally then, the constraint is the 2 subsets have equal size. And for the binary variables, step 2, we need to divide our nodes into 2 subsets, A and B. So let's use the binary variables to label our nodes. We'll say that x sub I, so x sub 1 is for node 1, for example. That'll be 1 if node 1 is in set A, and it'll be 0 if node 1 is in set B. And so binary variables are a natural fit with graph partitioning for this reason. They're either in one set or the other. And now we want to formulate the objective, and that is to minimize the number of edges between subsets. So what happens for a particular edge? Let's consider one edge between nodes 1 and 2. We know that the value of x1, that is for node 1, will be 1 if it's in subset A, and it'll be 0 if it's in subset B. And if you think about it for a second, if the qubits have the same value, they're in the same set. Whereas if they have different values, they're in different sets. And that's how we define the binary variables. We want the qubits to be in the same set. So to minimize the number in different sets, we can do that if all the qubits are in the same set, if we can make that happen. And so what we're going to do is penalize the solutions where the qubits are in different sets, so that anytime that happens, I'll pay a penalty, and I'll try to minimize paying that penalty. So in our problem here, in the truth table, you can see that I've put a penalty on the cases where the qubits have different values. In other words, 0, 1, and 1, 0. And the 1 is arbitrary. As we talked earlier in the last unit, you can do whatever number you want. As long as I penalize it, I'm going to favor the cases where they're in the same set. And in this way, I'm going to favor solutions which have as many as possible in the same set, and therefore as few as possible in different sets. The thing is, though, we've seen this before. In the last unit, we talked about how when we want edges to have the 2 qubits equal solution, when we want 2 qubits equal, this was this 1, 1 minus 2 solution, like x plus y minus 2xy. So therefore, for 2 qubits, x1 and x2, what I want is a formula x1 plus x2 minus 2x1, x2. And if you think about that for a minute, that will penalize the cases where x1 is 0 and x2 is 1, and vice versa, x1 is 1 and x2 is 0. Those are penalized, whereas the 0, 0 and 1, 1 solutions will be favored. But now, of course, I'm going to extend it to an arbitrary edge, xi plus xj minus 2xi xj. That will properly penalize the cases where the qubits have different values. And therefore, I can extend all the way to the bottom here to the mathematics notation for all I and j that are in the set of edges. That is my objective function. I want to minimize the sum of xi plus xj minus 2xi xj over all I and j where I and j are edges. And now I've got to deal with the constraint. The 2 subsets have equal size is the constraint. So an equivalent statement is that subset A has size V, where V is the number of vertices, divide 2. And so the size of subset A is, if I sum up all those x sub i's over from I to V, x sub I, that'll tell me the size of the subset. And this to me is very clever. I didn't come up with this, which is that if I sum up the individual x sub i's, I'll just find out how many are in subset A, because we made the assumption that if x sub I is 1, it's in A. So therefore, if I sum all the x's, I'll get the number in subset A. Very clever. So the constraint is the sum over I of x sub I is the number of vertices divided by 2. Why do we divide by 2? Because we're dividing into 2 subsets. Okay, so now in step 3, we talked about we have to make this mathematically workable. I wrote the objective here at the top, and then the constraint is the sum over x sub I is V over 2. So to make that QUBO appropriate, move it to one side, sum over, V over 2 minus the sum, and square to avoid negative values, just like we talked about earlier in the one hot problem and so on. The squaring makes it a parabola and gives it a minimum. And we simplify, we do the algebra. I have 3 terms now, and I'm going to remove the V over 2 divide 4 for the moment, but we will come back to it. And what I have left is minus V times the sum over xi plus the sum over xi squared. And here's the QUBO as it currently is. The sum over the I and j that are edges of xi plus xj minus 2xi xj, sum gamma, some Lagrange parameter, times the sum we just got from the constraints. But notice that that final term there, that sum over I x sub I squared, is not ready to be programmed. In other words, it's not QUBO ready because it's not a QUBO at this point. It's a sum and squared, and in order to do that, I'm going to have to work that sum out. So let's do that. Okay, if I write out this sum of x sub I squared, I'm just sort of writing it out in a lot of detail here. Some of you may be already familiar with it, but I encourage you to do this by hand on a piece of paper, whether you do the FOIL method or whether you write the one on top of the other. Just convince yourself that this algebra works, and this is the extent of the algebra that's required to write QUBOs. So in this case, I've written it on the first row as x1 times the whole sum plus x2 times the sum. And then we get to the next step. Notice there's going to be some squared terms and the cross terms, 2x1, x2, and so forth. When I work it out, I get every single individual x first, and this is in the third row, the x1 plus x2 plus x3, plus all cross terms. And then finally, at the bottom, I get an individual sum on xi plus a double sum of I and j to xi xj. And this is the sort of sum that Python is very good at. This is easy to write in Python to sum the loops like this. So we end up with a general graph partitioning QUBO at the top. When I merge all the terms that I've got, remember I had some with the minus v term coming in the sum multiplied in the constraints. I can simplify for a clique, which is the name of a fully connected graph. So a clique is a graph where any node has a direct coupler or connection to any other node. And if you do that on the bottom, there are 3 terms that result when we do that. And it's just a little simpler, although a graph partitioning on a clique, as we'll see, is less interesting than some of the more complicated graphs. But I want to focus on this for some of you who aren't familiar with this. We'll do an easier problem to understand at first. And if I write a program to do this, and put in gamma equals 1.5. That's the Lagrange parameter. And we do this on the clique that I showed at the beginning of this unit, the 4 qubits all connected together. I get 6 ground state solutions with energy -2. And when we do a QUBO problem, it's always really important to start by analyzing the energies and the solutions as much as we possibly can. So what are these solutions telling us? So here's the first solution, where I've drawn one of the subsets in blue and the other in red. Qubit 0 is 1, qubit 1 is 1, qubit 2 is 0, and qubit 3 is 0. Are the partitions the same size? Yes. How many links between the partitions? 4. Is this a valid solution? It looks like it is to me, right? Because the partitions are the same size, and I don't think, given the connectivity of this particular graph, I don't think there's any fewer number that I can get in terms of links between the partitions. So this does look like a valid solution to me. Now, for the full mesh with 4 qubits, we got 6 solutions of energy -2. And can you explain why we got that many? Just turn me off here again and think about it for a minute. Can you move those qubits around with the colors, that is, change who's blue and who's red, so that 2 of each? I think you're going to convince yourself that the 6 actually does make sense, that there should be 6 solutions. So let's do a little bit of energy analysis now. The problem is a competition between the 2 requirements. You're minimizing the number of edges between subsets, 0 connected to 1. Each such edge costs an energy of 1. That's that number that I set up, which was arbitrary. The subsets should be the same size, and the gamma term raises the energy if the subsets are not the same size. So can a solution satisfy both requirements? Yes. Choose one of our solutions and assess the following. Are the subsets the same size? How many edges are between them? Well, we found 4, and the subsets are the same size, and the energy was -2 in this case. But what does the -2 mean? In other words, if I had 4 and links between, why isn't the energy 4? Like, why is the energy -2? And this is where that constant comes into play. We forgot the constant, which was gamma v squared divided by 4. And if we calculate what that is in this particular problem, gamma was 1.5, v is 4, so that comes out to 6. If I add 6 to the -2s that I got from the energies for those ground state solutions, I do get a total of 4. That's the expected total energy. So everything works when we use that constant. And you don't have to, but if you make use of it, you can end up with a nice interpretation sometimes of the overall energy, which is a good thing. Now, as an exercise, I'll leave it to you to do this when you write your own program. Change gamma to some other number, and do you get the same total energy? I'm going to leave that for you to work out, and whether you should get the same total energy. Okay, now we want to move on to larger problems. 2 qubits is actually not going to get us very far. And so we want to think about bigger problems and how we might run them on the DWave LEAP system. And in order to think about what bigger problems mean, think about that as we went over in the last unit, the DWave quantum computer has a graph shape. In other words, there are specific qubits, and those specific qubits have specific couplers between them. And until someday when somebody builds a completely universal quantum computer, when you can solve any graph that you want, the shape of the graph in the problem might not be the same as the host graph. In other words, suppose I'm working on some computer where the host graph offers hexagons. And suppose I want to put a triangle onto a hexagon, so the top shape. I can do that in a number of ways. For example, I could tie 3 qubits together, the ones there in that middle plot. That would make 1 qubit, and 2 2s would make a qubit, and then 3 would make a qubit, and that would give me a triangle. It would act like a triangle on the host graph. But there's many ways to do this, of course. In the bottom one, I've replaced each individual qubit with 2 physical qubits. So 2 1s, 2 2s, 2 3s, and those will connect like a triangle on the hexagonal shape. So this all has relevance, and we're going to now talk about how we deal with this, which is a subject called embedding. And remember, in this case, we'll do a quick review here. The Chimaera graph looks like this, where you have this unit cell with a row 0, 1, 2, 3, and the column 4, 5, 6, 7, and links like shown here. And in the 2000Q, the native QPU topology is a Chimaera graph. In the case when we announce the Advantage system, it'll be a Pegasus graph, which looks a little bit different. But now we want to ask a question. And the question is, can I assign a physical qubit to each variable in a triangle on the Chimaera structure? In other words, could I embed a triangle onto the shape that is drawn here? And if you think about it for a while, there's no way to do it. For example, if you go across the top from the first one to the second, that is the left to the second one, there's no way to pick another single qubit where you could go and then get back to that one at the top left. And it turns out there's no odd loops in the Chimaera architecture. So, what if your problem needs a 3-loop? How would you do that? And here's a way to do it. Form a chain of 2 physical qubits. Constrain the qubits in the chain to have the same value. And that'll cause the 2 physical qubits to act like 1 logical qubit. And this is a graph subject called minor embedding, or just embedding. And you saw this a little bit before. That was the intent of that picture where we were embedding a triangle onto a hexagon at the beginning of this unit. We're going to connect, somehow chain or constrain the 2 qubits in the chain to have the same value. And that will cause the shape to be on top, to be embedded onto the graph that I have. And the subject in general is called minor embedding, and DWave offers minor embedding software, which is built into the Ocean toolkit. The main algorithm that's been in use for several years is called Makri Roy, after the 3 people that developed it. And this slide just gives you a little bit of the mathematical information about the algorithm. The main point is that the overall problem is NP hard. So we just do the best we can, and this algorithm does very well for hundreds of vertices. And so now I'm going to show you some examples of embeddings. So this is an 8-clique. You can see on the left there any node. If we pick 7, for example, it's got 7 links to all the other nodes in the graph. And on the right is the link, is the picture, the embedded graph, as it ends up embedded on Chimaera. And to interpret this, notice that each color, like let's say magenta on the far right, has 3 nodes chained together. So that is a chain of length 3, and this is where the Makri Roy algorithm embedded it. onto the DWave Chimaera architecture. And you can notice that there's others in there that are threes, the dark blue and light green and so forth. It looks like, in fact, oh, nope, the brown is a chain of two. The chains are not always of same length, but generally we want the chains to be not so long because it gets difficult to have them have the same value, which is required mathematically. And I didn't talk about how that's done, but that's part of what happens when you embed. The problem is you're putting additional constraints into the problem to get all of those nodes to have the same value physically so that it behaves like a single chain. It behaves basically like a logical qubit, as we talked about before. But let's now continue to look at some more pictures. And here's a 20 clique. So in other words, pick any node and you should be able to count 19 links, that's 20 minus 1, to all the others in the picture on the left there. And on the right is the embedding. And it looks to me like the chains have length maybe 5, 6, maybe a few more, 7 possibly. But you notice that there's a number of colors and they're beginning to use more of that Chimaera grid that I showed just a couple moments ago. The embedding has its job to try to spread out the problem's graph so that the chains don't go very long. And here I want to show you something interesting, which is embedding an 8 clique from a couple moments ago on the Pegasus structure. And as I mentioned, the Advantage, which will be released soon, Advantage architecture has a Pegasus infrastructure, which has a different shape, a different topology, and it has basically much higher connectivity. And we see when we draw the graph on Pegasus here that some of these particular nodes do not even have chains. In other words, like look at the bright green in the middle there. That one is by itself, and it looks like the dark green has 2, magenta has 2, the brown has 2, but red also is embedded on just 1. And so the Pegasus architecture, because of the way it was designed to reduce the chain length by providing a lot more connectivity. In the Chimaera graph, the degree is 6. In other words, each node is surrounded by 6 other nodes with couplers, and in Pegasus it's up to 15. So there's much more connectivity, and as a result, the chain lengths go down. And let's see another example of that here on a bigger clique. And here's a 20 clique embedded on Pegasus. And just as an example, notice the dark blue there, sort of center bottom and going up to the top. That's a chain of only length 3. And what we've seen is that the chains are much shorter. In this case, Pegasus uses about half the number of qubits. The chain length drops. This is going to lead to much better problem solving. So it's going to be very exciting when Advantage becomes available to see problems embed onto Pegasus with much shorter chains, and we expect the performance to be much greater, much better as a result. Now, recently, in the last few years, the embedding algorithm for cliques has actually been improved. And this is showing some work here by Kelly Boothby and Andrew King and Aidan Roy of DWave. Aidan Roy has left, but the other two are very much part of DWave. This was a work that was done in 2015 with a clique embedder. In other words, if you're embedding on cliques, there should be some advantages associated with that, and this paper shows that. And right now I'd like to show you some plots, some graphs of embedded cliques with the new clique embedding. So this is going to be a different algorithm than Kai, Makri, and Roy. And here's clique embedding an 8 clique on Pegasus. And the clique embedding, what I found so far in using it is that the graphs and the embeddings tend to be a lot more symmetric. The chains tend to be shorter, and the graphs that is the embedded graphs are just they look better. The chains are shorter, and they're embedded a little bit more cleanly with the new clique embedding. So it looks like very successful work. And I encourage you to try out the clique embedding when you run your problems. A lot of big problems in financial modeling, traveling salesman, problems like that use cliques. So the clique embedding comes along at a very good time for a lot of the production scale problems we're starting to see. So let's continue on now and talk about embedding and the DWave Ocean API. That is how you accomplish embedding within it and utilize it and explore it and so forth. So what we want to do is talk about an approach to using Ocean and using it to do embedding. We have a small program here which is in the middle of the screen, starting on the third line. And basically what you do is you define the QUBO there in the fourth line, right in the middle of the screen, the line with Q. And then you define a sampler. And the sampler gets wrapped in something called a composite. In this case called lazy fixed embedding composite. And what that does is it takes care of doing the embedding for you. It basically calls the software necessary to embed the problem that you provide, this Q matrix. And in the next line there, starting with response, basically you submit the problem to the quantum computer, the sampler, and it provides the embedding for you beneath the hood, which was taken care of when we called lazy fixed embedding composite. Notice the parameters that are going in there. The chain strength is passed in, and num reads. Num reads is the same as the number of annealing cycles that we're going to run. And one advantage to this particular way of doing it is that you can get the embedding back from the run. In other words, if I wanted to look at it, the line starting with print there, print sampler properties embedding, would give me the embedding that it used. It would show me which qubits this particular problem was embedded on. The last two lines there just are lines that take care of printing the output. So that's a problem very much like this, a program very much like this, is where I got those runs that you saw earlier in this presentation. And I put the call that you want to use up there at the top. So there's this notion of a composite wrapping around the sampler, and DWave sampler points to the QPU. And then when we say sample QUBO, that basically says run this problem from a given QUBO with these various parameters. So that's one of the approaches that you can take. So here's a second approach you can take is instead of relying on an embedding composite, you could use some software to do the embedding yourself. And so an example of that is here, where the composite in this case is called fixed embedding composite. Show the call in the middle of the slide. And you can see that it takes, in addition to a sampler, like the DWave sampler, it takes an embedding. And so that embedding is called on the line before, find embedding, where you give it the edge list from a real solver, for example, and the Q matrix, and it finds the embedding. And find embedding is from code called minor. That's another one of Ocean's packages. And fixed embedding composite uses an embedding that you have already found for the specific QPU. And so for people who have already studied embedding or are interested in utilizing particular embedding aspects, you may want to do that instead of using the Makri Roy embedding that we talked about before. So those two aspects are there, those two options are there, that you can either have it do the embedding for you or do it yourself. And to show you this in action a little bit, let's go back to a problem that we solved in the last unit, the friends and enemies. Only in this case, it's going to have a little bit of a different topology. Xavier, or X, is on the left. We want him to be friends with Yolanda. Yolanda, then we want to be enemies with Zeke, or Z. And then we want Z and X, Zeke and Xavier, to be friends. And if you think about this for a second, it's not possible. Can you see why? It's because if you have X and Y with the same value, like 1 and 1, and you want Yolanda and Zeke to have an opposite value, 1 and 0, then Zeke and Xavier can't get back to having the same value again. So this is an example of what's called a frustrated loop. And it's also a triangle, which is interesting. So what we're going to find is that there's no way to do this, and one of these relationships is going to get violated. So I wrote a little program to do this, and let's look at the results of that. And here's some typical results for this. In the red, you see the solutions look like, for qubit 0, 0, that's maybe X. For Y, 1. And for Z, that's 2, 0. And we see that if you do that, if we have this solution, the friend relationship across the top is not valid, but the other two are. In other words, 1 and 2 are different, and then 0 and 2 are the same. So this is called a one. It doesn't really have a name, I guess, but it's an example where there's one discrepancy in the three relationships. And if you think about it, we expect actually 6 of those that can change where the 0 and the 1s are, where I violate the relationships. And we do indeed see 6 lines with energy 0 there, where I've set the offset so that the energy comes out to be 0 for the solution. And notice that in the blue column to the right, that's the number of solutions out of 1,000 for num reads, which is about a 1/6 on average. The QPU is probabilistic, so we don't expect the same 6 every time, and we also don't expect to see exactly the same number for all 6 solutions. Notice at the bottom there, there's a couple of excited states that came into play where they violated 2 of the 3 conditions, friends and enemies. Notice also the final column is what is called chain break fraction, and that's the fraction of chains which did not manage to hold the values that we wanted them to. In other words, I talked earlier about how a chain is a set of qubits that have been constrained to have the same value, and this is telling us that we don't have any that do not keep the same value. But what we're going to do in the next few slides here is explore the chain strength a little bit. And now we're going to see what happens if we set the chain strength to something too low. So an example is if chain strength is 1/2, then you can see in the red there that the solutions don't make as much sense, basically. And there's also chain break fraction. In other words, see there, the chain break fraction on the right is 1/3, indicating that there has been a chain break. So the problem basically becomes something else. And so we clearly need to get the chain strength into a range where it's viable. And so the overall point is vary the chain strength to see what happens. Start with some reasonable value of it, and you can try to double it, whatever. Is there any sign of broken chains? And if there are, does increasing the parameter help remove them or reduce them in any way? And then the software I spoke of a couple moments ago utilize the newly available chain strength estimation methods to help narrow the range. And you include this DWave embedding chain strength package, and there are two methods called uniform torque compensation and scaled, and those will give you values in which indicate an estimate based on some calculation that ocean does on what it thinks the chain strength might be. And then you can also get the chain strength back from running with embedding composite using the syntax below at the bottom, printing response info, embedding context, chain strength. So all these things should give some range that the chain strength should be in. But you could still raise the same question, what is a reasonable value? In other words, even the software methods are indicating that we're just giving you a rough area. And Makri and Roy doesn't offer more than a large number, is what it says. And so the first attempt should be, the chain strength should be the same order of magnitude as the rest of the terms in the Ising and QUBO or QUBO model. And the reason for that is that when the problem is scaled, that'll guarantee that the forces keeping the member qubits the same will be comparable to all other qubit forces in the problem. But of course, it is problem dependent. And so what I said before about those software estimates are as good as you can do in a general sense without knowing more details of the problem. But I expect there will be a lot more research into this as time goes on, since this is an important parameter that has to be adjusted. So let's go with some conclusions from our studies in this second unit of practical quantum computing. Study the small problems, 1 hot, 2 qubits, choosing boxes to get started building QUBOs. And again, I'll make the point that even the small problems are vitally important for understanding how to set up the bigger ones. Utilize known problems like graph partitioning and the other ones formulated by Andrew Lucas in his paper. Utilize those and check your results. Make sure you're getting things that make sense to you. Be aware of embedding. Use the ocean tools to determine whether chains and broken chains might be affecting your problem. And watch hour 3 of this practical quantum computing series to learn about our hybrid solver service and advantage. And again, if you have any extra questions, comments, etc., it's Joel Gottlieb, jgottlieb@dwavesys.com. Thank you very much for listening, and I'll see you in the third part of the series.